mean, you've done some interesting stuff on what we call as opportunistic transmission, and let's hear what you have to say.
Okay, before starting my talk, I want to give my sincerest gratitude to my advisor, Professor Mary Amanda. Both this thesis and my personal development have benefited greatly from his guidance and insight. The title of my thesis is Opportunistic Transmission for Wireless Data over Fading Channels under Energy and Delay Constraints. So as we know, the information services have almost unlimited potential in the wireless environment. Most of today's fixed application will continue to make sense in the mobile environment, and a variety of new services are certain to evolve for people on the move. A fundamental characteristic of the mobile networks is the variation of the signal strength of the underlying communication links. Such variation can be due to the multipath fading, the path loss, distance attenuation, shadowing by obstacles, or interference from other users. In the traditional communication system design, this kind of variation is viewed as a source of unreliability that has to be mitigated. However, recent advances in the wireless communication theory suggest an opposing view, which is that the channel variation can instead be exploited by transmitting information opportunistically when the channel is drawn, either in time, frequency, or space. And so this modern view of the wireless communication opens up plenty of new research topics, especially for the data systems. Since data services can be supported by the intermittent connectivity, then we can exploit the delay tolerance inherent by designing the channel-dependent transmission strategies. One example is the Infostations. As we know, in the communication architecture of the Infostation systems, only small and separated islands of coverage provides low cost and low power, but high-speed access to information services in a mobile environment. Another example refers to the study on the capacity of the wireless ad hoc networks. It is shown that per user throughput can significantly increase asymptotically when the nodes are mobile rather than fixed. And this improvement can be achieved by exploiting the mobility of the nodes. While all these kind of strategies can improve system performance markedly, the energy conservation and the quality of the service guarantee are also major concerns in supporting heterogeneous data applications for mobile devices. Therefore, the limited portable battery energy and the delay sensitivity of the data services will also play important roles in the design of such kind of opportunistic transmission strategies. So in this defense, I will discuss a few problems analyzed in my thesis aiming at the energy conservation, battery management, and the quality of the service support. So here's the outline. And in my thesis, we only consider node-to-node communication situation. Actually, this models a single link of wireless communication networks and ignores any issues involving interference from other users. And this can be regarded as being characteristic of Infostation systems, because in the Infostation systems, the high-rate data service are provisioned mostly for one user at a time. So three problems I want the three problems I'm going to discuss here. The first one is a file transfer problem, which can demonstrate the design of the adaptive transmission strategies under both energy and delay constraints. And the second one is a energy constraint power allocations problem under the information theoretical consideration. And the third one is the energy efficient packet scheduling problem. And all these problems are set in a time-varying, slow-fading environment. And finally, I will give a summary and future work. And I have to emphasize here is in my thesis, we only consider single-user systems, and our major objective is to find energy-efficient transmission strategy, and the performance metrics include the throughput, packet loss, and the most important one is the communication delay. And here, communication delay can refer to the transmission delay, the coding and decoding delay, or the packet buffer delay in different communication scenarios. So we consider communication delay here. I list a few examples of the three types of delay constraints. The first one is no delay constraint. It corresponds to a situation where there's no constraint imposed on the total time in the information transfer. So it's suitable for the non-real-time services such as email or FTP. So the total time in the information transfer, we call it the communication window here, in this case can be pretty long. And the second case is we call it average delay constraint case, because of the randomness of the channel state or the birthness of the data source. If the transmission policy depends on the channel state or the data burst, the total time spending in this information transfer or the buffered time of the packet would be a random variable. So in this case, we only consider policies which can satisfy that the average communication delay is less than a preset threshold. And the third one is we call it soft delay constraint. It corresponds to a situation where some non-real-time services are implicitly subject to some kind of soft delay constraint. One example is when a user has its connection, the communication link, terminated randomly due to the movement outside a certain coverage area. So this communication window actually is a random variable which is independent of the user's actions. And an example could be that there is a delay penalty imposed on the communication time, which increases as the actual communication delay. And this delay penalty can be determined based on the emergency status of the information or the cost per time unit of the wireless link. And we will show that the soft delay constraint on these two examples actually have the same mathematical formulation under some assumptions. And the fourth case is a strict delay constraint. Here we only consider policies which can satisfy the explicit time deadline given by this D threshold. And for other types of delay constraint, for example, here is a probabilistic delay threshold can be guaranteed. But for this case, it is a little bit hard, kind of complicated to formulate mathematically. So in my thesis, we'll only consider the first four cases. Okay, so for the first problem, the file transfer problem. Many people have already studied the energy efficient radio resource management strategies such as power or rate control for the wireless data systems. But most of them consider the problem by assuming there's infinite information to be transferred and usually under the average power constraint. So in my case, we are going to analyze the power control problem to transfer finite size data files, say M packets altogether, and under total energy constraint, say E joules. And there are two performance metrics taken into consideration. The first one is the probability of success, which means the probability of successfully transferring the entire file of the packets within the energy budget. And the second one is the file transfer delay, which refers to the total time spent in this file transfer. So our objective is by giving the total energy and the file size, we want to find the optimal transmission policy that maximizes its probability of successful file transfer under different delay constraint scenarios. Okay, before I formulate our problem, I have to give some words about our fading channel model. Here, in the high-rate packet data system, it is reasonable to assume that all the channel symbols in one packet duration experience the same channel state. In other words, the received signal-to-noise ratio remains at a constant level during the entire packet duration. So here we assume the packet rate is constant. So we consider discrete system and one packet slot corresponds to this constant packet duration. So in each packet slot, the slow fading channel can be modeled as an AWG channel. And here X and Y are input and output signals, N is the AWG noise, and H is the fading attenuation factor. Then we define a sequence of fading attenuation thresholds denoted by this H0 to HK minus 1. By this, we partition the received signal-to-noise ratio into the finite K intervals. And if the channel is set on state Sk if this fading factor belongs to the Kth interval. So by this way, we define the finite K channel states. And considering the dependence between the consecutive packet slots, either the memory channel model of the correlated channel model can be defined. In this problem, we resort to a Markov chain to characterize the dependence correlation between the consecutive packet slots. And we assume the transitions between channel states only into the labeling of the same states because we assume it's a very slow fading environment. And the channel states on each state will specify one packet slot. So the transition probabilities between channel states can be approximated based on the Doppler frequency. So if we have fast fading, the higher Doppler frequency, we have the higher transition probabilities between channel states. So on each channel state, a certain packet aggregator can be approximated based on the fading status on this state. And if we do not consider any reliable channel coding here, the probability of correct reception of one packet is actually simply given by this equation. Here the BER is average bit error rate on the AWG channel by giving the fading status H and the transmit power P. And the actual function F is a probability density function of the fading factor. Because there's no reliable channel coding is considered here, so corruption of any information bits will cause error reception of the entire packet. And note that even on the best channel state K-1, the error reception of the one packet is still greater than 0. Then the transmission policy, this is giving the system model, and by storing all the M packets in the transmitter, a buffer, the transmitter tries to transmit packets consecutively, one packet per slot. So at the beginning time instant of each packet slot, we need to decide the transmit power for this packet, which is according to a power policy, and it's determined based on the channel state information feedback and the energy and the buffer status. And here we assume there's DC time units in the delay of the channel state information feedback.
Let me ask the question.
Yes.
Why doesn't this model take you to a 1-bit packet? 1 bit per packet.
That's really the
Right? You're saying that the packet error rate is
So then it's just average bit error.
no. I mean, this model should, right? It takes you to using a 1-bit packet, right?
Mm-hmm.
I mean, because of the fact that that's the best performance you'll get, right? If you make a 1-bit packet.
No, he's asking, what was it you was asking?
Yeah, I'm not saying it.
What will we use the packet?
Yeah.
Go back one.
He's saying if you try to optimize this model over the number of packets you should send in a number of bits you should send in any packet,
Should be 1.
he's saying it should be 1, and that's right.
Yeah, but we do not optimize it over because we just assume a data rate, and according to the Markov model, we have to set a data in a reasonable range.
Rate you can have any rate you want. You can have instantaneous feedback on, and you have this model for error.
No, but the key is delta T is given by whatever you call the channel.
Right.
So then the point is you sort of design your packets such that over the packet duration, essentially you see a constant rate.
Right.
So
if I did a 1-bit packet, that's guaranteed.
you guarantee that, but you could have more definitely. And
It's okay.
so I think the point is, I don't think he's trying to sort of optimize this
No,
model.
I was just saying, I think I was
This is just an abstraction of the channel. You're right though.
This is yeah. I mean, the simplification of the model leads you to kind of.
Yeah.
Yeah, that's
Okay. That's okay.
So as I said, we assume there's DC time unit delay in the channel state information feedback channel. And here, if DC equals 0, which means the transmitter have instantaneous perfect channel state information before we transmit this packet. And if DC equals some positive number n, which means the transmitter just has the channel state information n slots back. And here we use DC equals infinity to denote that the transmitter does not have channel state information at all. And since we do not consider any reliable channel coding in this case, we use the simplistic ARQ mechanism stop and wait scheme for the error control. So we also assume there is an instantaneous error-free feedback channel to inform the transmitter of the packet reception status. packet received successfully, or packet reception fails. So upon the immediate notification of packet reception failure, the transmitter has to arrange to resend the same packet until it's correctly received. So the transmission policy actually is a sequence of transmit power, and the transmit power usually is the function of the channel state information, the residual energy level, or the number of remaining packets in the buffer at the current time. So the transmit power usually is also a function of the system time. But for some policies, they are independent of system time, and such policies are called stationary policy. To simplify the mathematics further in this problem, we only admit two choices for these transmit power functions, and we denote it as A equals 1, action 1, which means we choose to transmit one packet in this slot with a constant power, and action not denoted by A equals 0, which means we choose to wait. We do not transmit anything in this packet slot. Then we can define two events here. That E1 denotes the event that all the packets are correctly transferred within the energy budget. And E0 denote the event that some packets have not correctly transferred when the communication is terminated. What?
Are any of your policies ever going to be stationary? I was wondering why you would.
It depends on the delay constraint.
Huh?
Depends on different formulations. We can get optimal results can be stationary or not stationary. Okay, so here we assume the communication is terminated immediately after we found that it is impossible to transmit all the remaining packets in the buffer by the residual energy or in the remaining time. So actually communication time window is the time interval start from the beginning time instant to the time instant either event 1 or event not occurs. So either we find event 1 or event not occurs, we immediately stop this communication procedure. And we also found that probability of successful file transfer actually is the probability of event 1 occurs by giving a transmission policy pi. So our problem here on the average delay constraint is to find the optimal transmission policy pi that maximizes the probability of successful file transfer. However, the average communication window has to be less than the preset threshold. And this problem can be formulated in the constraint Markov decision process and can be solved by the infinite horizon dynamic programming algorithms.
Well, did you say earlier, maybe I missed what the average communication window is?
Okay, so let's count the time from the beginning time instant to the time instant either event 1 or event not occurs. Event 0 means event 1 is okay, we'll transmit all the M packets. That's done, the job is done. And event not means job fails, either due to the short of the energy or short of time.
And so n pi is the number of steps you go.
Yes. So M pi actually is a random variable.
Until one of those two events.
Yes.
Okay.
So N pi actually is a random variable depending on the channel states and the policy pi. And for this average delay constraint case, we want the average number of the communication window is less than the preset threshold. Okay, and we said we can use the infinite horizon dynamic programming algorithm to solve this problem, and we found the stationary optimum policy does exist in this problem. And I do not want to give you very detailed mathematical deduction here, so let's see what the optimal transmission policy look like by numeric examples. Here, we use the 8-state Markov channel model that partition the channel with identical steady state probabilities. So as I said, A7 is the strongest state and A0 is the lowest state in a state. And we use the average delay constraint 45 packet slots. And in this numeric example, we assume this equals 0, which means the transmitter has the instantaneous channel state information. So So these two figures show two slices of optimal transmission policy when the residual packet numbers 18 and 5 respectively. Here the x-axis is the channel states and S7 is the strongest state, and the y-axis is the residual energy level. The shaded regions signify action 1, which means we choose to transmit one packet in this slot. And the white regions represent action 9, which means we choose to wait. So by observing this optimal transmission policy, we found that it is stationary. It does not depend on system time. And also, it is a function of this kind of threshold functions as the channel state, residual energy, and the residual number of packets in the buffer. Say
DC is is it the channel state information feedback delay?
yes,
Or,
which means there's no delay.
So you have instantaneous channel.
Yes. And for the, let's see, where we go. Okay, let's say if we have the more residual energy left, or we have less packet in the buffer, the optimal transmission policy actually is less selective. We can try to transmit on some packet, even on some low SR states, if we have more residual energy or have less packet in the buffer.
So you're able to prove that the policy is stationary, the optimal policy? Or is that an observation, or is it a...
Actually, we formulated this as an infinite horizon dynamic programming process, and we also can
Okay,
fun.
so
Yes. Okay, so okay, and this figure gives a minimum probability failure as a function of the Doppler frequency corresponding to different channel state information feedback delay, and the dashed curve corresponds to the channel independent transmission policy. DC equals infinity is the transmit anyway. We do not have any information. And as we observe that here, if DC decreases, which means the more accurate channel state information the transmitter has, the much higher probability of success for file transfer can be obtained. It suggests that the channel-dependent transmission policy can improve system performance significantly. And let's focus on this. If DC equals 0, which means there's no channel state information feedback delay, and we found that the fast fading results higher probability of successful file transfer. Because of fast fading, that is higher Doppler frequency, yields higher transition probabilities between channel states. So it implies that the channel may visit high ACR states more frequently. Although it also increases the probability of visiting low ACR states, but according to the optimal transmission policy, we do not transmit on those low ACR states, which we basically will almost transmit on the high ACR states. So within the finite communication window, the increase of the Doppler frequency or the increase of the transition probabilities will increase the probability of successful file transfer.
So Henry, physically, it looks like DC equals 1. It looks pretty good, right? But it's hard to understand physically what that means in relation to Doppler frequency. Of
Yeah, I will. Okay. For the DC, it's greater than 0. This case does not always true, because there is a trade-off between the channel estimation and the exploiting the channel fluctuation. Because say if
So I guess I'm asking.
I will.
You're gonna get to it? Okay.
Yeah, if DC, okay, let's say if DC equals 0, which means there's no channel state information feedback, and no fluctuation of the channel actually can bring more benefits to a system if we use opportunistic transmission policy by exploiting the nature given fluctuation of the channel by hitting the peaks. However, if DC is greater than 0, which means there's some delay in the feedback channel, it is a trade-off between the channel estimation and the exploiting the channel fluctuation. On one hand, we hope channel can vary very slowly, then we can have the accurate channel state information. On the other hand, we hope channel can fluctuate fast, then we can exploit the good channel state sufficiently by use of opportunistic transmission policy. However, in this figure, does not show this phenomenon because we use very slow fading channel model here. But in my thesis, I discuss a two-state channel model, and we will say And I discussed this case in more detail. Say if for certain transition probabilities, actually channel is independent or memoryless. Actually, the curve will be goes down as a channel independent transmission policy.
I think I'm asking something simpler.
Mm.
The units of DC, right,
Yes.
are in some units either packets or bit transmission times, right? Like 1 unit of delay is
Yes.
if you get the channel states at 1 bit later, 1 packet later.
One slot rate, one packet later.
1 packet later,
Yes.
right? And that packet has something to do, like that packet delay time, like that times the Doppler frequency is, what's the relationship between, is the Doppler frequency in units of that packet somehow 1 over that packet delay time? Am I making any darn sense?
No, you're asking a good question, but I don't think this model captures that right. See, this model, the Doppler frequency only affects the transition probabilities of this Markov model you have for the underlying channel.
Yeah,
Right? And so what Roy is asking is DC, is it somehow related to FD in the plots you've shown?
Well, it's sort of like,
How many milliseconds is DC? Right? How many milliseconds is DC?
Is DC
So that you can write FD times T and
Yeah, so the
know
question
something
asked
about
is,
it.
yeah, can you somehow,
I think it's a 0.1 millisecond in this example.
DC is 0.1 milliseconds?
No, this. Yeah, the T, the packet, one packet slot.
it's 0.1 millisecond?
No, it's 0.25 milliseconds.
0.25
So let's do the math that was simpler. I think it was 1 millisecond. So like your channel is like even at 80, right? Your channel is pretty much like you don't see a channel variation too much even in 5 or 10.
Yeah, because this model does not allow to use.
10 units.
That's what he, I don't know if you caught what he was trying to say. There is an example, he's worked out an example, right, for a 2-state model, only 2 channel states in the thesis, where he shows that you're not going to necessarily observe this trend where if you increase DC, right, it's not like you're going to keep decreasing with Doppler frequency, you can actually go back up again. He shows that it can happen. And that is the trade-off between channel estimation and exploiting channel variation. See, normally if Doppler frequency increases, right, your channel estimation should get worse.
Yeah.
So therefore, even though you can exploit the channel due to its variation, which is varying more, you don't have the correct information to do it. So there's a trade-off, right? And this model, that's why it doesn't show up on these pictures, but he created a 2-state example where he actually works it out and shows that. See, this whole sort of block, this finite, block fading model, right? Is actually a really slow fading channel.
Yes.
And sort of which is used by all these information theory results and.
But somehow wouldn't
all this stuff.
even in this model wouldn't the math turn around that like as FD got higher and higher, things eventually got
Then this
worse?
model is not accurate because according to this model, the transition probabilities should be much less than 1. Otherwise, if you get the FD which higher, the transition probability maybe is greater than 1. The model is just flat.
Transition probability is greater than 1?
If you choose a really big FD.
Remember
So
the
here we use
transition
just
probability
100
is a function of the
hertz,
Doppler
so
frequency.
transition probability is kind of slow.
So this block, that's what I was trying to say. The block fading model, right, has limitations in that it assumes that it is valid only under slow fading. So if you sort of arbitrarily increase FD to some say 1000 or 2000, that model just collapses.
Is the model collapsing because like you still turn all of the FD and everything, turn it into some Markov chain? Or is it that you don't get the
Because in this model,
you would jump from state to state?
You
or-
won't get a 1 state.
yeah, because we assume that we only transition to the adjacent state.
Is that really where things break down?
That's right. Because it's really slow fading. Otherwise, if we can the more generous Markov model, we do not know how to use Doppler frequency to approximate the transition probabilities between any channel states. So here we use a certain method to use Doppler frequency
So do you have an idea of what is the maximum FD that makes sense?
Yeah, I will check. Yeah, I will check that it generally is 0.1, 0.2. That's for the transition probabilities. Otherwise, according to
What is the FD?
What is the corresponding FD is asking?
if this one is 100 something like that, it's reasonable.
100 is, what happens when it's 200? It's not reasonable.
It's not reasonable. It's like I get some curves, but it's not reasonable. Maybe because the transition probability is 0.5, I don't think it's reasonable according to that model.
Okay, so that's why he made up this two.
Yeah,
that's why we made him
I wrote
to
it
do
in the
this
appendix.
two-state example, where you can clearly see this trade-off between channel estimation and channel variation.
Okay.
Just a quick, simple question. So, because we have feedback delay, right? Whenever you say channel estimation, because here there are two things. One is estimation of current channel, another is prediction of next state. So when you say estimation, do you mean both of them?
Yeah, we use the channel state information in slots back to predict the current channel state.
Yeah. So the estimation of previous channel is. Do you assume that estimation of current channel is perfect, and then you use this to predict? So there's a prediction error, or
No, we still only use the feedback information.
For instance, does the receiver make a perfect?
Yeah.
Oh,
Yeah, it makes it perfect.
And then there.
It's just a delay, but the information is perfect.
Yeah, and then you have some Markov.
Yes.
Model.
Okay, for the strict delay constraint case, the problem is similar. One is the optimal transmission policy that maximizes the probability of success. However, the exact communication window should be less than a preset deadline. And this problem can be formulated as a finite horizon Markov decision process. And we find the optimum policy is non-stationary. For the same numeric example, for the same channel state, and we use for the same Markov channel model, we use 100 packet slot as the time deadline, and these two figures show two slices of optimal transmission policy when the time equals 0 and 82, respectively, when the residual packet number in the buffer is 18. So as we see here, the optimal transmission policy on the strict delay constraint case is non-stationary. It changes from time to time. It's different functions from at time equals 0 and at time equals 82. Let's see if I equals 0, which means the transmission just begins. So the transmitter still has 100 packet slots ahead. So the transmitter can afford to wait for the better channel state in the near future. So at this moment, the optimal transmission policy is kind of selective. We only schedule this transmission when the channel is good enough. However, when I goes to 82 and there are still 18 packets in the buffer, and the transmitter gets desperate at this time, and it has to catch the last chance. So the optimal transmission policy is stipulates transmission everywhere.
This little L is what you started with? Is that the total length or the length that's left?
It's the length that left, right? But essentially, it depends only on that.
Right.
The policies depend only on the length left. So you can think of it if you want to as the
Yeah,
to start with or at the top.
Not on the energy.
It's left. It depends on all three. It depends on
Depend
three
on all the
variables.
functions. Yeah.
Channel state, residual energy, and the number.
Yeah, so optimal transmission policy actually is less selective when the residual communication window shrinks in the strict delay constraint case. And similarly, we can still assume in this figure probability of failure varying with the Doppler frequency, we can find that the more accurate channel state information the transmitter has, the higher the higher probability of success can be obtained. And for TC equals 0, still have the fast reading can be exploited by transmitting can improve system performance. Okay, so this is a file transfer problem, and in this problem we only consider a binary power control schemes, and we use a constant transmission rate. And when we consider more complicated system, the problem is how could we approach information theoretical limits if we given both energy and delay constraints. So the next problem I'm going to discuss is power allocation problem under information capacity consideration. And here we assume there's infinite information supply at the transmitter end, and we will use a similar finite state Markov block feeding channel model. And when we talk about the capacity for the feeding channels, there are a few capacity-related notions have been defined in the early work. The first one is ergodic capacity.
Glad you're here and not Andrea.
I know. See what he did to her name.
Claude Smith.
Oh, yeah.
They should call her Claude Smith or something even worse. Okay.
And the first one is ergodic capacity, which is defined for the non-real-time services, and it is defined as the highest achievable transmission rate for reliable communications. And the second one is the delay limited capacity. And we just, you see that just gave the reference number. And the next one is delay limited capacity, which is defined for the real-time applications. And with a constant code rate throughout the entire feeding process, it is defined as the highest achievable this constant code rate for reliable communications. And the third one is the outage capacity, which is very similar to the delay limited capacity, except allowing a certain amount of information outage. And most of this early work, to our knowledge, has preliminarily considered either no power constraint or usually under the average power constraint. But when with the average power constraint, the total consumed energy actually increases as the system time. When time goes to infinity, even with the finite average power constraint, the total energy goes to infinity also. So in our problem here, the total energy is strictly limited. And our objective is to find an optimal transmission policy which maximizes a lower bound of the expected sum of rates over the entire communication window. And I will give the mathematical definition of this expected sum of rates for different communication scenarios. Again, we can use a very slow feeding channel model here, different from the packet-oriented Markov channel model discussed in the file transfer problem. Here we consider a block feeding channel model, and one block consists of a batch of channel symbols, and we assume that in the slow feeding environment, the receiver signal to noise ratio remains a constant level during the entire communication block. So here the one time slot corresponds to one block, and in each block the channel can be modeled as an AWG channel, and we use the same method to define a sequence of feeding attenuation thresholds to partition the receiver signal to noise ratio and define the finite K channel states.
What's the difference in the two models?
No difference, only the units is different. One is per packet, one is per block. And it's also we use the same Markov chain to characterize the correlation between consecutive packet slots. Blocks, slot, and the transition probabilities depend on the Doppler frequency. And to discuss the capacity of the channel, we have to give more assumptions here. In this problem, we assume both the transmitter and the receiver have the perfect instantaneous channel state information. And in the typical block feeding channel model, in one block, a fairly large number of channel symbols can be transmitted to enable the reliable communications or to guarantee an acceptably small probability of error. So with a similar approximation here, we still can also assume that the energy consumed for transmitting one block of channel symbols is large enough but still finite. So with these two assumptions here, we can assume that the maximum throughput we can achieve in one block time actually is very close to the capacity of the AWG channel if using the optimal transmission coding scheme. So the one stage rate actually approximated by this equation. Here, note that we use, because we only have the finite channel state information feedback, we do not know the exact value of that feeding factor H. So we use a lower threshold of the corresponding interval to calculate this one stage rate because this rate can be definitely achieved if using optimal coding scheme.
Can you go back one slide?
This one?
Okay.
I don't like the third assumption at all. But you can't do anything without it.
The energy for one is large.
But once we assume this second statement is reasonable,
I mean, the whole capacity, the way he wrote C, right? But he wrote an approximate sign, that's okay. If you write log of 1 plus s, the energy is growing linearly as the number of symbols grow.
yes, but if you
And all your results are under the assumption that.
but we still say it's a finite.
Right, I know. No, I'm saying it's an assumption, but you know.
So long as the block time is
It's
finite,
questionable, but everybody,
and it should
you know.
be finite.
Because C, that log of 1 plus s is valid only under an average bar constraint, otherwise it's not. Right. So that is the only thing that I always sort of make myself unhappy thinking about that. But then I sort of convince myself it's okay.
But you still have a finite upper bound, you have a finite battery energy.
That you have, but you cannot write the expression log of 1 plus s to characterize something called whatever your performance metric. That can be written only, strictly speaking, only as the energy grows linearly with the window of communication. And all these results apply when the window is sort of. But here is what I learned. Sergio said, don't ever think it's infinite. Always think it's large. Use the word large. That's why he even has some notation. And for those of you taking this class, he has some notation. Remember? He's introduced some notation that says it's not really infinite, but it's basically large where all these results make sense. So from that point of view, it's okay.
Okay, the expected sum of rates on the no delay constraint case is given by this equation here. For the total energy is given by the E, and the expectation is over the channel states. So on each block, at the beginning time instant of each block, we need to decide the transmitted power for this block of channel symbols, and the transmitted power actually is a function of the channel state and the residual energy level. And so in each block, we transmit with a certain power, and we assume that the maximum throughput we can achieve is close to the capacity of the AWG channel, which means if the transmitted power is this PI and the transmission rate or coding rate is this amount of mutual information, and we assume this code word can be correctly decoded at the receiver end. Okay, so and another thing is for the no delay constraint case, the summation index is extended from 0 to infinity, even though the communication window is finite in the actually word, because when all the energy is expanded, the rate contribution in the subsequent terms are all set to 0. So the problem here is giving the total energy one for the optimal transmission policy that maximizes expected sum of rates. And another notion defined here is energy efficiency, which is by applying the optimal transmission policy pi star, the throughput can achieve per energy unit, which means how many information bits we can correctly transmit it per energy unit if applying this optimal transmission policy pi star. For the non-real time services, no delay constraint case, we have this theorem which tells us the optimal transmission policy calculates transmission only on the best channel state with an arbitrarily small power, no matter how long it takes to consume all the energy. And the energy efficiency in this case turns out to be a constant which serves as an upper bound of all the delay constraint cases. So for the soft delay constraint case, as we said, the communication window is assumed to be a random variable which is independent of the action of the transmitter. So let this communication window N follow a geometric distribution by giving this equation. Here alpha is the discounting parameters. So by this definition, we can say that in each block, the communication may be terminated with the probability 1 minus alpha. And expected sum of rates in giving this equation, and the expectation is over both the channel state and this communication window N. And it turns out.
Do you mind repeating the motivation for this constraint? I forgot. I think you mentioned that in the beginning.
Yeah, one is a case is a communication window may be randomly terminated due to the movement outside a certain average area. And another thing is
You dropped your laptop.
this expected sum of rates turns out to be this equation, and by observing this equation, as say here, alpha actually can be treated as a delay penalty. It is a word like discounted by a factor alpha in the subsequent blocks. So a lot of time you take the move penalty imposed on the communication, and the penalty is bigger when alpha is smaller. So we call this the soft delay constraint case, and our problem here is to find the optimal transmission policy that maximizes expected sum of rates.
You also have these abandonment models and stuff, people give up.
And some structural results of this solution of this problem can be given this theorem. The first one is kind of simple. If we have more energy budget, we can achieve higher expected sum of rates during the communication time. And the second statement shows if we increase the energy budget, we can increase the expected sum of rates, but however decrease energy efficiency. Actually, the total throughput and the energy efficiency actually is a conflicting metrics. And for this formulation of the problem, the stationary optimal transmission policy can be found. And the last statement shows us if we have the more residual energy at this moment, the higher transmit power we can use. Because in this case, the average communication window actually is finite. To utilize all the residual energy effectively, the transmitter may want to transmit as much as possible before the communication is terminated. So at this time, if with more residual energy, the transmitter is more confident to put more energy on the transmission to increase the expected sum of rates in a finite communication window. So also we give some more examples for this case. These two figures show the optimal transmission policy with different delay penalty alpha. The x-axis is a channel state. We still assume the H7 is the strongest state and is not is lowest state, single state. Y-axis is the residual energy normalized by the block time, and z-axis gives the optimal transmission power in watts. And as we observe these figures, we find that in contrast with the optimal transmission policy on the no delay constraint case, the optimal transmission policy on the soft delay constraint case does not stipulate transmission only on the best channel state. We still choose to transmit on some low excess states. The reason, just as I said, in the finite average communication window, we have to utilize the energy as much as possible before the communication is terminated. So sometimes we would rather transmit on some low excess states.
Henry, it looks like for constant residual energy, if you go across the graph that way, like the best channel state is channel 7.
Yes.
Like it seemed as though you have both. First, the power is 0, right, for the really bad states. Then it goes up because the states are getting better, right? And then does it dip back down, like in the power, in say like when residual energy is 4 and the state goes from 4 to 5 or 5 to 6, does it actually go down and then go, like is there a ripple in there if I were to plot those powers across there?
It's not. The optimal transmission policy is not the increase function as the channel states.
It's not an increasing function.
It's not. I discussed this problem in more detail in my thesis. Actually, the major problem is there's a correlation between the channel states in this model. If we assume it's a memory channel model, it's an increased function, monotonic function of the channel states. But however, if there's correlation between the channel states and the communication time is finite, we cannot show it's increased or not. It's not monotonic.
Is that somehow because if you're in a really good state, you know you're going to stay in really good states for a while, so you have to back off a little bit because you know you're going to be pumping, sort of? I don't know. Like it's better.
That's
to
yeah. That's
doing-
an explanation, sure, but I don't think you can show anything sort of
Interesting.
linguistically.
Yeah,
But what I'm seeing is not just a. I mean, I was sort of asking first. It's not a.
I mean, he was motivated by
my
this picture,
eye.
right? He just wanted to make sure that this didn't sort of drop as you went across.
Yeah.
So,
But there is some ripple there, right?
yeah. Maybe you should add a figure that shows one of those profiles just to sort of see how much the ripple is. You can just take a slice, right, across say 4, residual energy 4 or 5, and then show sort of.
Yeah.
You can see it at 10, right? You can see it clearly.
Huh?
Yeah, at
10
10
you
can
can see it clearly, right?
Oh yeah.
Yeah, he's
okay.
right. Indeed.
Right.
10 you can see sort of the.
So if you're in a particular state, how can you predict whether your state will be better or worse afterwards? So if it was a good enough state from the previous state, I will just transmit as much as I can.
No, but your
You've
policy is
got a model.
optimized to do some average metric. So it's not a question of.
Just in this
It's
instance.
on average. This is what you.
Okay, and also if alpha is smaller, which means the average communication window is shorter, we stipulate more transmission on the low SR states to utilize the residual energy sufficiently. And this figure gives the energy efficiency varying with the Doppler frequency. So we can find that the fast feeding or the more fluctuation of the channel can benefit us or could help us to transmit more information bits per energy unit. Okay, for the strictly constrained case, we have a similar problem by giving the total energy E and the time guideline N sub T. The expected sum of rates is given by this equation. And the problem is similar. We found the optimal transmission policy that maximizes its expected sum of rates. And the similar theorem can be found here. But in this strictly constrained case, the optimum policy is non-stationary. Okay, so these two figures actually show two slices of optimal transmission policy when system time I equals 0 and I equals 450 if the time guideline we choose 500 block time. As we said, it's different from time to time. It's a non-stationary policy. Say if I equals 0, which means the transmitter still can wait, so we just choose to transmit on almost fast two channel states. And if I equals to 450, the desperate transmitter has to transmit some power on the lowest states. And this figure is similar for the strictly constrained case. The more fluctuation of the channel can be exploited by opportunistic transmission policy to achieve higher energy efficiency. And another thing is we want to build some connection between the energy constraint power control problem and the average power constraint power control problem. So here let's consider a strict delay constraint problem with a delay constraint ND and the energy budget is capital E, which is ND times the average power constraint. So if we let this ND goes to infinity, so does this total energy budget. However, this average power constraint P average is fixed. So our energy constraint power control problem actually tends to be the average power constraint power control problem. And the optimal transmission policy tends to be a stationary policy, which is actually we have no water feeding scheme over the finite feeding states. And our expected sum of rates, maximum expected sum of rates, approaches ergodic capacity. So by this analysis, we can see the average power constraint power control problem actually is a asymptotical case of the energy constraint power control problems. So this is for this problem. And in these two problems we ignored the dynamics of the data source. So the next problem I'm going to discuss is a scheduling problem for the wireless, packet-oriented wireless node, where a certain arriving statistics is taken into consideration to capture the dynamics of the data source. And we use a similar finite state block filling channel model, and we consider the performance matrix average of an infinite communication window. And similar work has been done by Raja, Sabara, and Ajahn at Rice University, and they consider also the single user system, and performance metrics include the average power, average buffer delay, and the packet loss rate. And they found the optimal transmission policy that minimizes the packet loss on both the average delay and the power constraints. And they also proposed a suboptimal policy. However, the parameters on each channel state are different. They have different set of parameters on each channel state. And in this work, I will propose a much simpler suboptimal policy and give the corresponding queuing analysis to use a simpler approximation for the policy design. Firstly, there's a system model. There's a finite buffer size at the transmitter end with L packets, capacity, and a certain data source sends packets consecutively in this buffer with the rate lambda packets per block time. At beginning time instant of each block, we residual UI packets from this buffer. However, on RI packets are transmitted. RI packet assembled, encoded, and transmitted with a constant transmit power PI. So note that there are UI minus RI packets are directly dropped at the transmitter end, and I will explain later why we choose drop packets instead of transmitting them. And the values of these RI, UI, and the PI are determined based on the scheduling policy, which is based on the channel state information feedback and the queue length. So the transmission policy actually is a sequence of triple vectors: residual rate, transmission rate, and transmitting power. And in each block time, more than one packet here can be encoded and transmitted. And our objective is to find the minimum average, to find the optimal transmission policy that minimizes average transmitted power under both the average buffer delay and the packet loss constraint.
What is SAR?
What is
SAR.
SAR.
SAR is assembling, assembling and SAR is segmentation and reassembly.
Segmentation and reassembly.
Yes.
Yeah.
So basically, you're going to admit RI and throw away UI minus RI.
Yes.
Okay. And like the part you throw away is going to be state dependent. Like somehow the throwaway that is some state dependent thing.
Yes.
All three. The
Yes.
policy is URP. So all three
Yes,
will
it is
depend on the
state
state and the queue.
Yeah.
Channel state and the queue.
Okay. The P is power, right?
Peace out.
Okay.
So in each block, we assume that minimum required power for reliably transmitting RI packets are given by this equation. Here we use the relationship between the power rate relationship of the AWG channel capacity, because we assume that volume and large enough channel symbols can be transmitted, so the throughput is close to the capacity of the AWG channel. But in real time, we do not have to use this formulation. We can use any concave function. Yes, of the transmission rate. And the performance metrics include the average transmitted power, average buffer delay, and the packet loss. Packet will get lost into different scenarios. Firstly, if the transmitted power is less than this minimum required power for reliable transmission, the packet will never get correctly decoded, and we do not retransmit them. So those packets are denoted by the outage rate. And remember, some packets are directly chosen to be dropped. So those packets is characterized by the dropping rate. And for the final buffer size, if the buffer overflows, some packets will get lost, and which is denoted by the block rate. So our problem is to find the optimal transmission policy which minimizes the average transmitted power, however subject to the average buffer delay and the packet loss. For this average transmitted power minimization problem under the finite control space and the system space, it is known that there always exists a stationary optimal transmission policy. That means that the optimal transmission policy does not depend on system terms, they are just functions of the channel states and the Q length. And also we can derive the Borel theorem.
The PD is sort of the probability some bit of the information stream goes into the trash can, right?
PD, yes, drop.
PD for drop, right?
Yes.
PB
It's a block rate.
where are things getting blocked?
Because we consider the finite buffer size.
Buffer at the source.
Yeah.
Show the picture again.
So PB is things, the lambda going into that buffer of size L. Probably the L is that all else.
It's full. Yeah. So
And
overflow.
then P out. What
P out is the outage rate. If the transmitted power is less than minimum required power for reliable communications, will never get decoded correctly. So we assume that part of the packets will get lost.
P out is given by the capacity formula.
Say the P out is
Minimum power
is
you
less
need to
than
get.
minimum required power. We assume this minimum power for a certain error probability. If less than this power, we assume that packet will get lost.
So there's no ARQ.
There's
on it.
no retransmission.
But more than that, there's no loss in it. There's no
Right.
loss
Yeah.
in the power.
If it's more than this minimum required power,
It's reliable. It's reliable
can
decode.
get it.
Technically, those three numbers may or may not be less than 1, right? The sum of them. Like P out, you're sort of calculating an outage probably, given that something actually gets to the like it's conditioned on something else, right? For a packet that shows up over here, right? The P out you calculated, given it's over here and it gets into the transmission part, it's probably there's an outage in there and it's lost, right?
Yeah, I will show that for the optimal transmission power factor, P out is always equals to 0. And all the dropping rate and the block rate is divided by all the arrival packets.
So because you have perfect channel state.
Yes, we have perfect channel state. So this theorem actually tells us the minimum optimal transmission power is always minimum required power for reliable communications. In other words, that to conserve the transmitted power, to drop packets directly is more efficient than transmitting them but without enough power, because all these packets will get lost anyway, so we all the transmitting them to waste some power. So our problem is kind of simplified. Is the three functions is simplified to two functions. We only need to find the dropping rate and the transmission rate. But by observing this optimal transmission policy, there are some drawbacks. One of the major drawbacks of this optimal policy is it requires a sophisticated table lookup for implementation. And secondly, because we choose drop some packets after withdrawing from the buffer, use the later theorem to calculate the average buffer delay is not accurate. And the third one is the computational complex of the dynamic programming approaches is huge. It increases exponentially with the buffer size. And the optimal policy is very complicated to use some queuing analysis to derive some simple approximation of bounds to simplify the system design. So the next step, we are going to design a suboptimal policy where no packet is allowed to be dropped. And we use threshold rules to approximate this optimal transmission policy, which is defined only by 3 parameters. The first one is buffer size, denoted by L, and the second one is the channel state threshold. If the channel is worse than this threshold, we do not transmit anything. And the third one is we call this transmission-related threshold. If the Q length is less than this threshold, we transmit all the buffers, all the packets in the buffer in one block time. If the Q length is greater than this threshold, we use this constant rate, transmit RA packets per block. So our policy is further simplified to the 2 functions, to the 3 parameters. And our problem is to find the optimal parameters to minimize this average transmitted power subject to average delay and block rate here, because no packet is allowed to be dropped, so packet loss only happens when buffer overflows. And to solve, and the solution of this problem we call the suboptimal policy, and it can be solved by the dynamic programming approaches or use possible queuing analysis. And by dynamic programming, first we give some numeric examples first. First, we will assume the number of random packets in one block time of this Poisson distribution, and we use 8-state memory channel model here, and we assume that the 500 kilobits per second packet stream. So this figure shows that minimum average power varying with the average delay constraint under both suboptimal policy and optimum policy when the packet loss is restricted under 10 to the minus 7 and 10 to the minus 3 respectively. Here we can find that pink one actually is the suboptimal policy and the red one is the optimum policy. And we can find that the difference between the minimum average power of suboptimal policy and optimum policy is less than 0.5 dB. It suggests that the suboptimal policy can work pretty well to save the energy. And another thing we observe is even though we relax this packet loss constraint from 10 to the minus 7 to 10 to the minus 3, no much energy we can conserve. However, for different packet loss constraint, the required buffer size decreases significantly, which means by the relaxed packet loss rate, we cannot save much energy, but we can use much smaller buffer size to simplify the system design. So the next step, I wanted to try to use queuing analysis to analyze this problem. The system uses suboptimal policy. If you're giving these 3 parameters, you want to use these 3 parameters to calculate the performance metrics directly without using any dynamic programming approaches. But to use queuing analysis, we have to assume that there's a memory channel model. So in each block is independent. And we assume this Poisson arriving packet. So this transmission system under this simplified policy can be modeled as this queuing model here, which is a single server system with Poisson arriving customers, batch serving ability with finite buffer size and constant service time. So by using this queuing model, actually we can use the embedded Markov chain technique to find some method to evaluate the performance metrics.
So when when I was looking through this, if you use this embedded Markov chain,
Yes.
then I don't see why you actually have to assume this independent block.
Because we have used the vacation. When the channel is less than the threshold, we call it vacation, means the server does not serve any packets. If it's correlated, it's very hard to find the vacation time. If it's independent, so in each block, next block can be independently be a vacation. That'd be much easier for us.
I mean, if you have the correlation structure and you can figure out how these vacations happen, then you can use this. You're right. But it's, as Henry's
But
pointing
it's
out,
much
it's very hard to sort of figure out those things. So if you have the independent model, then readily you can say a vacation happens in the
Fraction of the time.
Okay, so for this embedded Markov chain technique, we assume that Qn is the number of packets at the departure time after every block of transmission, and this Qn forms a Markov chain, and the steady-state probability can be easily obtained. And you can use the steady-state probability of this embedded Markov chain to evaluate this block rate and average transfer power. But for the average buffer delay, we can derive the upper bound simply by this equation here, by introducing some certain approximation in the queuing model. So, but just give the
Where is the buffer playing? Where is the buffer?
Here, buffer, actually, we do not use buffer. Here, we assume buffer is infinity. When we use a buffer, the average buffer delay is always less than this upper bound. Right?
Do I go to my usual questions? I'll ask them how you calculate average delay when things are dropped.
Yeah.
For
You
this
should.
one?
You
For
should.
this
You
one?
should.
For
You should.
for
This is
tuning
his
also?
talk, right? He's given so far in his life. You should ask him.
So the things are getting dropped here, right? With
No,
the
there's
buffer?
no dropping. It's only block.
Things are getting blocked,
Yes.
right?
Yes.
So the average delay is for things that are admitted.
Yes. That's true. Once you get mated, you have buffer delay. Otherwise, you don't count this delay.
All right. So I guess, do you think of those guys as having zero delay or infinite delay?
That's the big.
Well,
Zero delay.
I don't
But
see
you're right.
zero.
It's infinite.
I don't know actually, but
No, I mean, they never make it anywhere. They never see the daylight anywhere.
but
so-
we do not count that part of delay in
It's a
average.
it's a
But
standard
for this
equation, right?
upper bound is assume there's a infinite buffer size.
Yeah.
So this upper bound does not have any second problem. But if for the final buffer we do not count that packets get lost, this is always the upper bound for the average delay we count. Actually, the delay actually is from the received buffered point of view. If packet get received, how much delay in the buffer and how much delay maybe during the transmission. If the packet never get received, we do not know how much.
Higher layer protocols might think differently.
Yeah.
Since you have this, picture at the bottom here, let me ask one question over here.
Mhm.
You see that? So that HA, right? That's where that's the
Channel state.
channel state, right? And the RA is the rate corresponding to that channel state.
No,
No.
just pick a number.
There are three independent parameters.
Yes. My objective here is giving three parameters. We want to find the easier way to calculate it.
And this the only reason that you pick a fixed RA is because as opposed to a RA that depends on the channel state. It's just for simplification.
No,
No, RE does not depend on this.
No, that's what I'm saying. You said RA beyond HA. You don't.
The H, this,
For at better states you don't transmit at the rate that
yes, that depends on
that
the H.
channel that
Yeah.
state will bear.
Yeah, RA is only defined when the H is greater than HA.
Right. But it's not higher for each higher state.
No, which is a constant. Right? The RA is all the same for all the states greater than this HA.
And that's because you just were trying to have a simple policy, or there's a reason to not
because
have a
it's-
higher rate at the
because
higher.
it's easier to use Q analysis. But
and not only that, I think it's a much simpler design, right? If you sort of look at his results when he showed the comparisons of the suboptimal policy to the optimal one. The optimal one, exactly, you have to keep, essentially, it's a very sophisticated lookup. And it really blows up exponentially with all these different state variables that you put in there. So it's just a much simpler way of trying to come up with something that works, I think, pretty easily.
So for the new examples here, we draw the average buffer delay as function of the transmission rate threshold. We fix the channel state threshold, and L goes to infinity, makes the very big buffer size. And we draw the results by running the dynamic programming approach and by the Monte Carlo simulation at the same time. And these two results should be the same. But there's a little bit difference because the accuracy of the dynamic programming or the Monte Carlo simulation. But theoretically it should be the same. And upper bound, we draw this less than red dash curve. We can see the upper bound is kind of tight and less than 0.5 block time. So, which means we can use this upper bound directly to estimate this buffer delay. And for the packet loss rate and average buffer, we have similar results. The left figure shows the packet loss rate varying with the buffer size when fixed to the RA and HA. And the right figure shows the average power varying with the transmission rate threshold RA when HA is fixed. So, and we gave all the results by dynamic programming, by the Monte Carlo simulation, and by the queuing analysis. You can see the queuing analysis gave the results very close to the simulation and by dynamic programming, which means by using embedded Markov chain technique, it's very effective to have this much simpler way to evaluate the performance metrics. So once
The
you
key thing in that queuing analysis is using a vacation model for the channel state. Is that a vacation that there's an independent, it goes on vacation?
the vacation is not really hard. The hardest part of the queuing analysis is a batch service. Because we can, if we serve one packet at a time, the steady state probability actually, steady probability at the departure rate is actually the same as the steady probability from outside observer. However, if batch is greater than 0, which means we serve more than one packet at a time, the steady probability by the embedded Markov chain is different from the steady state probability observed by an outsider. So we cannot use the steady probability directly. We just transform in some case to calculate the average power and the packet loss. We avoid finding the real steady state probability from outside observer. That's the hardest part for this queuing analysis. But if we simplify the problem by transmitting one packet at a time, the things will get much easier. Okay, let's summarize my talk. So in my thesis, I discussed a few examples of opportunistic transmission problems with aiming at with focusing on the energy conservation and the quality of the service support. Specifically, they are the energy efficient or in energy constraint delay sensitive file transfer problem and the energy constraint power allocation of the information theoretical consideration and the energy efficient simple packet scheduling scheme with both the packet delay and packet loss constraints. And in the thesis, I also discussed opportunistic transmission problem for the transmission control for randomly working mobile under the microeconomic modeling. But this problem, the formulation kind of simple, so I do not discuss this problem in my defense here. So I have to emphasize that the essence of the opportunistic transmission technique actually is to exploit the dynamics of the systems. The dynamics can be the channel variations in time, frequency, or even in space, and all the percentages of the data source. But in my thesis, we only consider this variation in time. So here's some future work we can do possibly. And as we said, the impact of this channel variation on the wireless communication network permeates throughout the layers from physical layer to the network layer. So at the physical layer, we can do some power control and channel coding, as I did a little bit for the timing in the time domain. And in the frequency domain, we can use opportunistic transmission to find the frequency selective fading. Or in the multi-antenna system, we can use a variation between the transmitter and receiver antenna pairs. Or for the multi-antenna system, we can even exploit the multi-antenna or use the beamforming technique to induce artificial variation when there's little natural given fading. And in my thesis, we only consider single user system. However, the opportunistic transmission technique is also very powerful when viewed in the broader context of the multi-user, multi-scale systems. One example is like the smart scheduling problem by design optimal scheduling policy, which can share the limited network resource while guarantee the individual quality of the service for single user. And another problem like the energy efficient routing in the ad hoc networks, or even the admission control several hand of problems in the control layer. So all the problems discussed in my series actually should serve as a starting point of designing wireless communication networks of the future. Okay, so that's it. And last, I want to thank all you guys to come for my devices. That's it. Any questions?
Any question? No? Okay. So let's
I'm tempted to ask.
No, you should ask.
No, it's okay.
So what is the
I think
picture?
you're being honest when
Yeah.
you made that big list of all the other places people could do research, and
Yeah,
and you were nice enough to not pose any impossible problems as much as
My problem actually, I have these slides. I really want to show you. Actually, the problem is maybe more practical to solve right now. Here is, say, for other type of delay, remember that probabilistic delay threshold. Maybe we can use some risk-sensitive control technique. We do not only minimize or constrain the average delay. Maybe we can figure out some utility function to include the expectation of the delay and the variance. And for the unknown, if we don't know the channel statistics, we can use some reinforced learning method or the PDP, which is partially observed Markov decision process. Maybe it's possible to solve this problem.
Whatever. You want to talk to me? We can make a mistake.
And for the multi-user system, actually, this is what I'm doing with your line. Right now, is we consider either the centralized scheme or the decentralized scheme, whichever is possible, to fight the multi-access interference. And in the end, the multi-antenna systems, maybe I will going to discuss it in the future. Is because this MIMO is kind of popular thing, everybody knows about that. So I think it's also possible use to exploit the flexibility of the diversity, complexing, and big form, or multiplexing and big form. And I think this kind of problem is maybe more practical, can solve. I have maybe a more clear way to solve it.
You can stay here and work on all this, you want to?
Which is, we have about
I'd
next
be
few
more
months.
than happy. All right, any other questions? Okay, so we should thank Henry then. Okay, so we should talk here only, right? I think the other room they might be keeping food.
Yeah, we can go.
Or should we go grab a sandwich and bring it here, or?
Or
Sanjay,
go in there, have
you're
a
not
sandwich.
hold on.
Yeah, I want to-
Keep your view graphs up. He wanted to ask
I want to
you
just
a
spend
couple
Okay.
Yeah, sure.
just go that last problem, right?
Mhm.
The last one that you're talking about. So, when the buffers are large, right? So how come the delay doesn't build up? It's not like you have that really large buffer with the 10⁻⁷ loss.
Right.
Then why